Hello everyone, I am Dr. Veenadhari, working as an associate professor from Rabindranath Tagore University. Today we are going to discuss about the instruction level parallelism from the subject Advanced Computer Architecture. The main objective of this video to know the importance of parallelism in system improvement and how to analyze the parallelism using the dependency graph. These are the main objectives, and after this video the students will be able to understand what is the importance of parallelism and how dependency graph will be able to understand the parallelism. Dependency graph, how it is important for analyzing the instruction level parallelism. So friends, normally formal definition of parallelism is if you want to execute two or more tasks or processes concurrently or simultaneously, then it is called parallelism. For normal understanding, using one example, suppose if you are working in an office. In an office, somebody is doing the stuffing of envelopes. For stuffing of the envelopes, what are the different tasks they need to do? First of all, he needs to identify the order of the letters. Next, he needs to fold the envelope letters, and after that he needs to put the envelopes letters into the particular envelope. After that, pasting the address. So that particular work is divided into different tasks. If these tasks will be performed by one only by one person, then it is called sequential task. If these work will be divided into 4 tasks and 4 persons are doing simultaneously or concurrently, then it is called parallelism. So parallelism will improve the performance of a system drastically. In a computer science system architecture, parallelism is the new dimension. Parallelism will be implemented in many ways: bit level parallelism, task level parallelism, and instruction level parallelism. We are mainly focusing on the instruction level parallelism, how to implement the instruction level parallelism, and how can we analyze the instruction level parallelism. In short form, it can be called as a ILP. Now coming into the instruction level parallelism, like formal definition of parallelism, instruction level parallelism is a measure. That means from a particular piece of code, how can we analyze the parallelism implementation. That means 10 instructions code, 5 instructions, suppose if you are implementing the parallelism, that means only 50% of parallelism is existing in that particular code. But how can we know by looking at the code? How can we analyze it? How can we analyze the instruction level parallelism from a particular piece of code? So don't worry, using the dependency analysis graph, we can analyze the instruction level parallelism from a particular code. See, this dependency graph analysis will be categorized into 3 types: data dependency, control dependency, and resource dependency. What is dependency? Suppose in a piece of code, 10 instructions are there. That means first instruction is dependent on the second instruction, or second instruction is dependent on the first instruction. We need to analyze it. So first of all, the first dependency is data dependency. So data dependency is again categorized into 3 types: flow dependency, anti-dependency, and output dependency. So now first dependency is flow dependency. Look at the example. 2 instructions are there, instruction I and instruction J. Look at that example. So first instruction I is having the instruction that is A is equal to B plus C. That means we are adding the 2 variables B plus C and we are storing in the output variable A. Here look at that. The first instruction output is feeding as the second instruction, is acting as a second instruction input. So that means it is flow dependent. Instruction J is flow dependent on the instruction I. That means after the completion, execution of the first instruction only, second instruction will be executed. So this type of dependency is called flow dependent. So what does it mean? If two instructions are flow dependent, that means we cannot execute it parallelly. It must be executed sequentially. That's why we need to identify the different types of dependencies in instruction level parallelism. So flow dependency will be denoted with the arrow mark. Okay. So second dependency is anti-dependence. Anti-dependence means it is the reverse of the flow dependence. That means first instruction input will be acting as a second instruction output. So that is the flow dependence reverse. That means whatever may be the dependency, these two instructions also, look at the example, instruction J and instruction I, these two are the anti-dependence. Okay, these don't worry, I will explain it with the one example. And the third dependency is the output dependency. Output dependency means, suppose if you are having the two instructions, you have three instructions, but those two instructions are using the same output variable. Look at the example, there A is the output variable. So same variable we are using for the instruction I and instruction J. So what will happen? So which instruction, which output will be storing on the A? So these two instructions are output dependent. So we cannot execute these two instructions parallelly. It must be executed sequentially. So that's why we need to identify the different dependencies using the instruction level parallelism using dependency graph analysis. Now look at the example I am going to explain with this. See here, four statements are available, that is S1, S2, S3 and S4 statements. Using this piece of code, we need to draw the dependency graph. So look at the example, there is a dependency graph. We have already drawn it. So first of all, identify the flow dependence from these particular statements. So look at that picture, that is S1 and S2. These two statements are flow dependent. Why it is flow dependent? So look at there, the first statement's output is register 1. The second statement input is also a register 1. That means the first statement output will be acting as a second statement input. So these are all the flow dependent. Can you identify some more dependencies from this piece of code? Can you able to identify? Look at that, statement 3 and statement 4. These are also flow dependent. Why it is flow dependent? The same situation. R1 is the output for statement 3 and R1 is the input for the statement 4. That's why it is flow dependent. Look at the graph, statement 1, statement 2 and statement 3, statement 4. These are denoting with the arrow mark. Next, we will look at the output dependence. So statement 1 and statement 3, these two are the output dependent. Why is it is output dependent? These two statements are using the same output variable, that is R1, register 1 they are going to use. So that's why in that graph also we are denoting with the output symbol S1 and S3, these are the output dependent. Next, can you able to identify the anti-dependent statements? Look at the code. S2 and S3, these are anti-dependent. So why it is anti-dependent? For S2, register 1 is a input variable. For S3, register 1 is a output variable. So that's why these two are the anti-dependent variables. So why we are drawing this type of dependency graph analysis? So what will happen after drawing this? How can we identify this using the dependency graph? How many statements are parallel and how many are sequential? So by looking at the graph, can you able to identify that S1, S4 are the independent statements. That means there is no dependency existing between these two statements. So that's why we can execute it parallelly. And one more statement, look at the graph, S2 and S4. These are also independent statements. These are not, there is no dependency existing between these two statements. So S2 and S4 also independent statements. So from this graph we can identify S1, S4 or S2, S4 we can execute parallelly, and remaining statements we can execute it sequentially. So you can using the dependency graph we can analyze it. Here 50% of parallelism is existing. Coming into the next example, here look at the graph and example. Here 8 independent tasks are available. These are denoting with the T1 to T8. So look at the task 1 to task 8, and dependency graph also we have drawn. See that that's T1 to T8, there is a dependency analysis, flow graph is available. So from this graph we need to write the parallel code. Parallel code will be starting with the begin and end. So in that we will see the first task is T1 and T2 can be executed parallelly because there is no flow dependency between these two tasks. Next, look at that, what are the different and some more tasks we can identify to execute parallelly. Those are T5, T6 and T7. There is no dependency between this. So that's why, so co-begin, co-end, in between that we can identify T5, T6, T7 and T1 and T2. So 5 instructions we can execute parallelly, and remaining 3 instructions will be executed sequentially. That means the measure of this particular task parallelism is 5 by 8, that is 60% parallelism is existing here. Okay. So next, coming into the next dependency, that is control dependency. So after analyzing the data dependency using the 3 dependencies, output dependency and flow dependency and anti-dependency, now we are coming into the control dependency. So in a particular code there are some segments. Segments means using the control structures or subroutines, functions. These are called some segments. If we want to execute those segments independently, that means parallelly, then we can achieve the parallelism. But sometimes using the control structures there will be dependent variables. Look at the next slide, that is control dependence. In that control dependence, count, I have used some piece of code, the count variable I am using. So until the runtime of our execution time, we cannot able to identify what is the value of count. So look at that, for loop is using the 100 times it will execute. After the execution only we can identify what is the value of the count. So the count variable we cannot use independently in other segment. Okay, so this using this count variable we cannot execute it independently. So this is called the control dependence. Okay, next coming into the resource dependence. Resource dependence. Resource dependence means what? Sometimes in parallel processing we are using some different processors to execute the instructions, but those processors are sharing some arithmetic logic units or control or some functional integer units. But here it cannot be in a sharing resources. Sometimes there will be some dependency will be existing. So we need to avoid those dependencies using the resource dependency analysis. In control dependency, Bernstein, one scientist, he identified some conditions. Some conditions he identified. Those conditions are, suppose there are so many processors. Processors will be denoted with P1 to Pn. Suppose n processors are there. Those processors will be denoted with P1 to Pn. But in this processors, each processor will be having the input set and output sets. Input sets will be denoted with the I1 to In and output sets will be denoted with the O1 to On. Okay. Bernstein identified three conditions. What are those three conditions? Look at the slide. So here the first set inputs and second processor's outputs cannot be matched. That means I1 intersect O2 is equal to 5 is equal to 0. It should be null. First processor inputs and second processor outputs cannot be matched. And the next condition is second processor inputs and first processor outputs. Inputs and outputs cannot be matched for the two processors. What we are going to check the parallelism. And the third condition is outputs also cannot be matched. That means if you are using the two processors, that O1 intersection O2, output 1 and intersect output 2, it is equal to 0. That means null value. It should equal to null value. Note down the value. That means note down here the point is inputs can be matched but outputs cannot be matched. Outputs and inputs cannot be matched. See here, don't worry, I am going to explain with one example. You can easily identify the parallelism from the process piece of code. So these are the conditions advised by the Bernstein. Okay. Now look at the example of parallelism using the Bernstein conditions. Here 5 processors are available. So these processors is having the some piece of code is here. So now from these 5 statements, we need to identify which processors we can execute parallelly and which we need to execute sequentially. Look at the code. So for example, I am taking the processor 1 and processor 2. So what is the code of processor 1? C is equal to D into E. And next code is M is equal to G plus C. Look at that. First processor output is C. Okay. Second processor input. What is the input? G and C are the input variables for the second processor. So it is matching. That means C input is there and for processor 1 C is an output. So we cannot execute P1 and P2 parallelly because it is matching. Okay. And next suppose P2 and P3. If you see that P2 and P3, so here there is no matching between the inputs and outputs. Okay. But you can ask, G is a common variable for this. But G is an input variable. So I have already told you inputs can be, we can take common, but it should not be common outputs and inputs. So here P2 and P3 can execute parallelly. After analyzing these conditions, these statements using the Bernstein conditions, so only P2, P3 and P5 is possible because they are all independent. But P1 and P4, P1 and P2, P4, they cannot be executed parallelly. They can only execute sequentially. So next look at the graph also. I am using the same example. So see here, if we are executing it sequentially, there will be 5 levels we need. First we need to execute parallel 1, process 1, process 2, process 3. Sequentially I am telling, okay, explaining. Next look at the second picture. The second picture, so we have already identified P2, P3 and P5. These we can execute parallelly. So only 3 levels we need. First we will execute the processor one. Next we already identified P2, P3, P5 can execute parallelly. So executed parallelly, and next is the P4. So how many levels we need here? 3 levels. So drastically the levels are reduced. Okay. So here we are improving the performance of a system by reducing the levels. So this is the importance of the parallelism. So but parallelism cannot be achieved it freely. And that means we need to implement some support from the hardware and software also. So this is the main instruction level parallelism is the important type of the parallelism to achieve the parallelism in a system for improvement of the system performance. Thank you very much.